somewhere out there, your own shadow could fall on a world with no sun to cast it. Close your eyes and picture the dark between the stars, not the soft dark of a bedroom at night, but a deeper dark, one that stretches for trillions of miles without a single point of light to break it. Now picture a planet out there, alone. No sun warms its face. No moon reflects a borrowed glow across its surface. It simply drifts, silent and unseen, carried by nothing but the momentum of its own long fall through space. Astronomers call these rogue planets, or sometimes free-floating planets. They are worlds that once may have circled a star, the way our own Earth circles the sun, until something cast them loose. If you stood on the surface of one of these worlds, your body would feel a cold beyond anything on Earth, a cold that creeps toward absolute zero, the point where atoms themselves grow almost still. There would be no horizon glowing pink with sunrise. There would be no warmth on your skin, ever, from any star. Above you, the sky would hold thousands of pinpoint lights, stars scattered like frost on black glass, and not one of them would be brighter or more special than the rest. Somewhere among them might be the very star this planet was born near, the one it left behind. You would have no way of knowing which one it was. This is the grand question we sit with tonight. How many planets like this exist, cut loose from their stars and wandering the space between them? Some researchers believe rogue planets may actually outnumber the stars in our galaxy. That is a strange thing to hold in your mind as you drift towards sleep. For every star you can imagine, there may be more worlds than that, drifting nearby, unseen, unlit, uncounted, one small thing before we drift further out. The universe has a new wonder for you every single night here. If you'd like, one waiting each evening, subscribe and let it find you. The idea of a planet without a star feels almost impossible at first. We tend to think of planets as things that belong to a sun, the way a leaf belongs to a tree. But gravity is not always gentle. In the crowded, chaotic years, when a solar system is young, planets can tug on each other with tremendous force. Sometimes, those tugs build up until one planet is flung outward, faster and faster, until it slips past the reach of its star's gravity entirely. From that moment on, it belongs to no one. It becomes a wanderer. We do not know exactly how common this is. Some models of planet formation suggest that ejections like this happen often, perhaps even more often than planets that stay put in stable orbits. Other researchers are more cautious, noting that our evidence is still thin, gathered from only a handful of confirmed detections and a wider set of indirect clues. The truth is that we are still learning how to even find these worlds, since a planet with no star to reflect light is almost invisible by nature. It shows up, if at all, as the faintest bend in starlight, or a brief flicker in a survey of the sky that took years to record. If you tried to imagine standing there, the silence would be the first thing you noticed. Not silence in your ears, since space carries no sound at all, but a deeper stillness, the absence of any daily rhythm. No sunrise, no sunset, no seasons turning the ground from green to gold. Whatever light touched such a world would come only from the stars themselves, or perhaps from within the planet, if it still held some heat left over from its birth. Your eyes, given time in that darkness, might adjust enough to see the ground beneath you by starlight alone, grey and dim and endless. We will spend this night moving slowly through what we do know, and what we still only guess, about these solitary worlds. We will ask how they are born, how they might hold on to warmth, and whether anything at all could survive on one. We will wonder whether the nearest such planet might be closer to us than we think, quietly passing through our own corner of the galaxy right now, unnoticed. None of these questions have full answers yet. That is, in a strange way, the comfort of it. Tonight is not about certainty. It is about letting your mind rest in the presence of a mystery too large to solve before sleep finds you. A mystery made of cold worlds and colder distances, drifting, patient, alone in the dark. Picture, for a moment, a young solar system. It's crowded and busy. Nothing like the calm and settled sky we know today. Several planets, maybe more than survive to this day, are swinging around a newborn star. They pull on each other with gravity, the invisible force that makes any two objects with mass reach toward one another. In a young system, that pulling can turn rough. If you could watch this happen from a safe distance, you would see slow, patient chaos. Nothing moves quickly on a human scale, but over millions of years, close passes between large planets can build up speed like a push on a swing that grows a little stronger each time. One planet may swing near a giant world, larger than Jupiter, and steal some of its motion. That stolen speed can be enough to carry a planet away from its star forever. Astronomers call this process gravitational ejection. It sounds harsh, but it is closer to a kind of cosmic sorting. Some planets settle into stable, lasting orbits. Others get flung outward, faster and faster, until they cross a line where the star's gravity can no longer pull them back. Once a planet crosses that line, it does not return. It becomes what scientists call a rogue planet, free of any star, drifting on its own through the space between. Your body standing on such a world would feel nothing dramatic in the moment of release. The escape itself would take thousands of years, far too slow to notice. But the result would be total. No more sunrise, no more warmth arriving each morning. Only the planet, and the dark, and whatever heat still lived inside it from its own formation. We think this happens often. Some models suggest that for every star with a stable family of planets, there may be one or more worlds that were once part of a system and got cast out early on. Jupiter itself, in our own solar system, may have wandered closer to the Sun, and then retreated, possibly flinging smaller worlds outward as it moved. This idea, sometimes called the grand tack, is still debated, but it points to something important. Even our own tidy-looking solar system carries scars from a rougher, more violent youth. There are other ways a planet might slip free, and researchers do not agree on which happens most. One idea involves a passing star. If another star drifts close enough to a young solar system, its gravity can pull a planet loose, almost like a bigger hand, reaching into someone else's game and taking a piece off the board. This kind of close stellar encounter would be rare, but stars are patient, and rare events add up over billions of years. A different possibility does not involve an established star system at all. Some rogue planets may never have belonged to a star to begin with. Clouds of gas and dust, the same raw material that forms stars, sometimes clump together on their own, forming objects with planet-like mass that never ignite into starlight. If this happens, the planet is not ejected. It simply forms already alone. Both paths, ejection and lone formation, may be happening across the galaxy at the same time, and there is no way yet to know which one produces more wandering worlds. If you tried to picture the size of these planets, you would not need to imagine anything strange. Many rogue planets, as far as we can tell from the ones detected so far, seem to fall in a range from smaller than Earth to many times the mass of Jupiter, Worlds several times heavier than Jupiter can still be lonely. Mass alone does not decide whether a planet keeps a companion star. It only takes one hard shove at the right moment, in the right direction. What remains unresolved is how common each cause really is. We do not have a clear count of how many rogue planets came from violent ejection versus quiet, independent formation. We also do not know how many planets in our galaxy have suffered this fate at all, though later sections will look closely at attempts to estimate that number. The evidence so far comes from scattered detections, computer models of young star systems, and careful guesswork built from physics we trust, but cannot yet fully confirm at this scale. For now, it is enough to hold this simple image in your mind. Somewhere, a planet that once had a sun in its sky now has none. It did not choose this. Gravity chose for it in a slow and silent motion that took longer than any human life. The planet drifts on, unaware, carrying whatever warmth remains from its birth, moving through a darkness with no edges and no end in sight. Picture a star system in its early years, when the planets are still finding their places. If you could watch it speed up, like a slow film played fast, you would see something like a dance floor that is far too crowded. Big planets swing wide arcs around the young star. Smaller ones drift between them, tugged this way and that. Nothing has settled yet. Nothing is calm. This is the early chaos that many scientists believe gives birth to rogue planets. In a young solar system, gravity is not gentle. It pulls and pushes in ways that are hard to predict, especially when several large planets share the same space. Some worlds get thrown into close, tight orbits near their star. Others get flung the opposite way, out toward the cold edges. And some, if the timing and the angles line up in just the right way, get thrown out completely. If you were floating near one of these young systems, you might feel the ground of a planet shudder faintly under you. Caught in a slow game of cosmic tug-of-war, it cannot win. A single close pass by a larger planet is often enough. The smaller world picks up speed with each gravitational pull, like a marble rolling faster down a hill. Eventually it moves fast enough to break free of the star's pull entirely. There is no dramatic explosion. There is only a quiet crossing of an invisible line, a moment where the planet stops circling and starts leaving. Astronomers call this process ejection, and it is thought to be surprisingly common. Some models suggest that almost every planetary system goes through a period of instability while it is young. Giant planets, especially ones close in size to Jupiter, are the most likely to do the throwing there. Gravity is strong enough to fling smaller neighbors into deep space. In a strange way, the smaller planets may owe their freedom to the size of the very planets that pushed them out. But ejection by sibling planets is not the only story. Another idea points to the star system itself, and to what happens when two stars pass close to one another, while planets are still forming around them. If a second star drifts near a young system, its gravity can reach out and steal a planet away, or fling it outward with a force the home star cannot counter. This kind of stellar flyby may have been common in the crowded star-forming clusters, where many stars are born close together, shoulder to shoulder, before slowly drifting apart over millions of years. There is a third possibility that some researchers find just as compelling. Not every rogue planet may have started life orbiting a star at all. Deep in the clouds of gas and dust, where stars are born, smaller clumps sometimes collapse under their own weight, the same way a star does, but never gather enough mass to ignite. These objects may form freely, drifting from the very beginning, never claimed by any star's gravity. If this is true, then some rogue worlds are not exiles. They are wanderers by birth, never having had a home to leave. The honest answer is that we do not know which of these paths is more common. It may be that all three happen in different systems at different times, shaped by whatever mix of stars and planets happens to be nearby. The math behind planetary ejection is quiet but relentless. Small shifts in distance, small differences in mass, can decide whether a planet stays bound to its star for billions of years, or slips away into darkness within a few million. What is clear is that this process takes time, sometimes tens of millions of years, as gravity slowly reshuffles a young system until it finds a stable pattern, or loses a planet in the process. The planet that leaves carries nothing with it but its own mass, its own heat, and whatever atmosphere it managed to hold onto during the encounter. If you stood on such a world during its final moments near its star, the sky would still show a fading point of light, growing smaller with each passing year, its color and warmth slipping away into the same emptiness the planet is now entering. Somewhere between 50 and 200 billion stars fill our galaxy alone, and if even a fraction of their systems produced a single rogue planet in their youth, the numbers could be staggering. No one knows the true count. What we do know is that the process which creates these drifting worlds is not rare or strange. It may simply be one of the ordinary costs of being born into a young, crowded, restless system, still learning how to settle down. If you could hold a rogue planet in your hands, it would feel like any other world at first. Rock, metal, maybe ice, the same stuff that makes up Earth, or Jupiter, or the moon outside your window. This is one of the quiet surprises of a planet with no sun. It is not made of anything strange. It is made of the same elements scattered through every corner of the universe. The same iron and silicon and carbon that gathered together long ago into every planet we know. Think about the iron sitting at the center of the Earth. That iron did not begin here. It was forged inside a star, cooked slowly through nuclear fusion, then scattered into space when that star died in a supernova. The same is likely true for a rogue planet's core. Somewhere, a star lived and died, and its ashes drifted through a cloud of gas and dust until gravity gathered them into a new shape. A world without a sun still carries the memory of the sun that made its ingredients possible. Water follows a similar path on Earth. Some water probably arrived early, folded into the rocks as our planet formed. Some may have come later, carried in on icy comets that struck the young planet like slow rain. Researchers still debate exactly how much came from each source. It remains an open question, one of the many small mysteries tucked inside our own world's history. A rogue planet, if it holds water at all, may carry the same layered story. Ice in its crust, ice in comets that once fell onto its surface, back when it still had a star to orbit. This is the part that can be hard to picture. Every rogue planet almost certainly began life close to a star, inside a spinning disk of gas and dust, just like Earth did. It gathered its water, its rock, its metals, under the light of a young sun. Only later, through some gravitational shove from a passing planet or a close call with another star, did it lose that light for good. The world, drifting in silence, now once had a sky. It once had days. If you stood on such a planet, the ground beneath your boots might feel almost familiar. It might be basalt, dark and glassy, the kind of rock that pools from lava on any young world. It might be layered with frozen nitrogen or methane, gases that would be invisible vapor back on Earth, but freeze solid in a place this cold. Without a nearby sun to warm it, The atmosphere a planet once held can slowly fall out of the sky, settling onto the surface as frost. Your breath, if you could breathe here, would form a mist that fell rather than rose. Some rogue planets may hold on to thicker atmospheres, especially the larger ones, close in mass to Jupiter. A bigger planet holds gravity strong enough to keep gases from drifting away into space. Hydrogen and helium, the lightest elements in the universe, might swirl around such a world in thick clouds, the same gases that made up the swirling storms of our own gas giants. Smaller, rocky rogue planets have a harder task. Their gravity is weaker, and their air, if they had any, may have long since turned to frost or escaped into the dark entirely. Whether any rocky rogue planet still holds a thin atmosphere is one more question researchers cannot yet answer with certainty. What is easier to say is this: every rogue planet is built from the same forge as every other planet. Carbon that once lived inside a star, oxygen born in the heart of another star that exploded before our own sun was born. Nothing in the universe is entirely new. Even a planet, cast out into the dark, cut off from any star, carries pieces of ancient starlight locked inside its rock and metal. It is a strange kind of company, knowing that a lonely world still shares its origin with everything else that shines. There is comfort in that thought. Even as the mystery stays open, we do not know the exact mix of elements inside any specific rogue planet, because we have never gotten close enough to measure one directly. We infer their makeup from what we know about planet formation elsewhere, and from the handful of gas giants we have glimpsed drifting free. If you drifted near one tonight, your body would settle into cold that has no comparison on Earth, surrounded by a world built from the same quiet materials as your own. Familiar ingredients, unfamiliar silence. A planet made of starlight, wandering now without a star to call its own. Picture yourself standing on the surface of a rogue world. No sunrise will ever come, no warmth will ever fall on your shoulders from above. The forces that once shaped this planet's short life near a star are gone now, and what remains is a quieter, colder set of rules. Gravity is the first force worth sitting with. It is the same gravity that held this planet close to its star once, and the same gravity that eventually let it go. In a young star system, gravity does not act alone or evenly. Every planet pulls on every other planet, gently at first, then more forcefully as orbits drift and cross. A close pass near a massive world can bend a smaller planet's path enough to fling it outward, faster and faster, until the star's pull can no longer call it home. This is called gravitational ejection, and it may be common enough that lonely worlds outnumber the stars that once held them. Once free, a rogue planet still carries gravity within itself. Its own mass keeps it round, keeps its insides pressed tight, keeps any moons it managed to carry along still circling faithfully in the dark. That inward pull never left. Only the outward tether to a star is gone. Heat is the next force to consider, and it behaves differently than you might expect. Some scientists believe a planet like this holds on to real warmth deep inside, left over from its violent birth billions of years ago. Radioactive elements buried in the rock decay slowly, releasing a faint but steady heat, the same kind of heat that keeps Earth's core molten today. If you dug far enough beneath the frozen crust of a rogue world, you might find rock still warm enough to flow. That heat has nowhere to escape too quickly, since no starlight adds to it, and no starlight competes with it. It simply seeps outward, slow and patient, over eons. Whether that inner warmth is enough to matter is still an open question. A rocky world the size of Earth may radiate its heat away faster than it can renew it, cooling toward the temperature of space itself, close to absolute zero, over long stretches of time. Day. Planet built more like Jupiter, thick with gas, and far larger, might hold its heat much longer, glowing faintly in infrared light for billions of years. Your body, on such a world, would feel a cold beyond anything Earth has ever produced, a cold with no wind chill and no relief, because there would be no atmosphere moving to carry that cold to your skin in the way you know it. There would simply be stillness and cold everywhere at once. Magnetism is another quiet force worth wondering about. A planet's magnetic field usually comes from motion deep inside it, from molten metal churning as the planet spins. That field does not depend on a nearby star to exist. Some rogue worlds may still carry their own magnetic shells around them. Faint, invisible sleeves stretched around the planet, deflecting the rare charged particle that drifts through interstellar space. Without a solar wind to push against, that shell would sit calm and mostly unbothered, a private shield with almost nothing left to shield against. Pressure and tides matter too, but only if a rogue planet is not entirely alone, if it kept a moon or two during its long fall out of its home system. The gravity between planet and moon can squeeze and flex the planet's interior with each pass. This is tidal heating, the same slow kneading that warms certain icy moons in our own solar system, enough to keep oceans liquid beneath their frozen shells. Some researchers wonder if this could be the key to warmth on a rogue world, a private furnace with no need for sunlight at all. Others point out that many rogue planets likely travel without any moons left, having lost them during the same violent ejection that cast the planet out in the first place. Which is more common remains unknown. Radiation from outside is nearly silent here. No solar wind streams past, no ultraviolet light bathes the surface, no steady rhythm of day and night ever governs anything. The only radiation reaching a rogue world comes from the ancient, faint glow of the cosmic microwave background, and from starlight so distant and thin it could never warm a single grain of dust. If you stood there and looked up, the forces shaping your world would not come from above at all. They would come from within, from the ground beneath your feet, patient and slow, the last living warmth of a planet that once had a sun. Close your eyes and picture the clock on your wall. Now imagine that clock stopped moving forever, its hands frozen at some quiet hour, and the room around it lost all sense of morning or evening. That stillness is close to what a rogue planet knows. There is no sunrise there. There is no sunset either. Without a star to circle, a wandering world simply has no day and no night. Only one long, unbroken dark that never changes. On Earth, a day is a rhythm your whole body understands, even in sleep. The planet spins once every 24 hours, and that spin gives us the soft transitions of dawn and dusk. A rogue planet may still spin on its own axis, so a single point on its surface could face first this direction, then that one. But turning in the dark is different from turning under a sun. There is no light source to reveal the difference. If you stood on such a world and watched the horizon for 100 of its rotations, you would see the same total blackness over and over, with no line of gold ever rising to greet you. To feel the distance involved, picture our own solar system shrunk down to something you could hold. If the sun became a basketball sitting on a table, Earth would be a peppercorn resting about 26 yards away. roughly the length of 2 school buses parked end to end. Neptune, the most distant planet in our system, would be a small marble almost a third of a mile from that basketball. Now, imagine a lone world drifting even farther out than that, so far that the basketball sun shrinks to a single point of light indistinguishable from any other point of light in the sky. That is the scale a rogue planet lives at. Its former star, if it had one, is just another anonymous speck among thousands. Some researchers estimate that rogue planets could outnumber the stars in our galaxy, though the true count remains genuinely unknown. If that estimate holds, there could be billions of these unattached worlds drifting through the Milky Way alone, each one carrying its own silence across unimaginable distances. Other scientists caution that our surveys are still too limited to know if the numbers are truly that high, since these worlds are so faint and so hard to catch in the act of passing by. The honest answer, for now, is that we are estimating in the dark, guided by small clues and educated guesses rather than a complete map. Temperature offers another way to feel the scale of this loneliness on Earth. A cold winter night might drop to 0 degrees Fahrenheit, cold enough to make your breath freeze in the air. A rogue planet's surface, cut off from any starlight, could fall close to absolute 0, the coldest temperature theoretically possible, hundreds of degrees colder than anything you have ever felt on skin. At that temperature, gases you breathe every day, like nitrogen and oxygen, would not stay as gas at all. They would settle onto the ground as a thin frost, coating the rocks and dust in something like a permanent silent snowfall that never melts. And yet, even in that deep cold, some planets may not be entirely without warmth. A large rogue world, several times the mass of Earth, might hold on to heat left over from its own formation, heat that has been slowly leaking out for billions of years. Scientists compare this to a coal that has been pulled from a fire and set aside. It cools slowly, glowing faintly from the inside, long after the flames are gone. If a rogue planet is massive enough, this residual heat, along with the slow decay of radioactive elements deep in its core, might keep a thin layer of warmth alive far beneath the frozen surface, even while the outside sits near absolute 0. If you stood on the surface of such a world, your body would feel nothing pulling you toward morning, nothing announcing evening. Your eyes would adjust to true darkness, the kind broken only by the pinprick light of stars too far away to warm you. Your skin would sense the cold pressing in, steady and complete, with no season ever arriving to change it. There would be no version of noon to look forward to, no sense of time passing in the sky above you at all, only the ground beneath your boots, and whatever quiet heat might still be rising slowly from somewhere far below. If you could stand on the surface of a rogue planet, the first thing you would notice is the ground itself. Not soft, not warm. A crust of frozen gas, packed tight and pale, stretching out under a sky with nothing in it. Some scientists picture nitrogen ice, plain and smooth like old wax. Others imagine frozen CO2, layered in thin sheets that crack and shift as pressure builds beneath them. Either way, the surface would hold no color the way a sunlit world does. No blue oceans, no green fields, just shades of white, grey, and something close to bone. Without a star to warm it, a rogue planet loses its lighter gases first. Hydrogen and helium drift off into space over long stretches of time, slipping away like breath in cold air. What stays behind depends on the planet's size and how tightly gravity holds on. A small, rocky world might end up nearly bare, its atmosphere long gone. A larger one, closer to the mass of Jupiter, might keep a thick shroud of gas wrapped around it, insulating whatever heat remains inside. This difference matters. It shapes whether the surface is a dead vacuum or something closer to a frozen greenhouse, sealed shut. Your body would feel the cold before you saw anything else. Surface temperatures on a true rogue planet could sink close to absolute zero. The coldest point physics allows, somewhere near minus 273 degrees Celsius. At temperature, gases that we breathe as air on Earth would fall as snow. Picture flakes of solid nitrogen drifting down in slow motion, settling onto dunes that never feel a warm season. Some researchers wonder if that snowfall happens in cycles, tied to whatever faint heat leaks up from below. Others think the surface may be locked in permanent stillness, unchanging for millions of years at a stretch. That question, where any warmth comes from at all, sits at the center of the mystery. A rogue planet has no sunlight to heat its surface, so any warmth must come from within. Radioactive decay in the core, the same slow process that keeps Earth's interior molten, could still be quietly working inside a wandering world. Leftover heat from the planet's formation, sealed in like a coal that never fully cools, might also linger for a long time. If a moon still orbits the planet, tidal flexing, the gentle stretching and squeezing caused by gravity, could add its own gentle warmth, kneading the interior like slow hands working dough. None of this would reach the surface as anything you could feel standing there. Whatever heat exists would most likely stay trapped far below, under kilometers of ice or frozen rock. On the surface itself, you would find only silence and cold, a stillness so complete that no wind moves and no sound carries. If the planet kept any atmosphere at all, it might be too thin to scatter light, since there is no light to scatter in the first place. The sky above you would hold no glow, no haze, nothing but scattered points of starlight, each one just as distant and indifferent as the last. Some researchers pictured jagged terrain shaped by ancient tectonic movement before the planet lost its star. Cliffs of frozen material, cracked and refrozen many times, could rise into sharp glassy ridges. Others suggest a smoother world, worn down slowly by the drift of frost across the surface. Without wind or rain in the way we know them, the physical shape of a rogue planet remains mostly guesswork, built from models rather than direct observation. Nobody has stood there. Nobody has watched the light fall, because there is no light to fall. Your eyes, if they could somehow survive the cold, would adjust to almost nothing. Just a slow shift of starlight as the planet turns, if it turns at all, since some rogue worlds may have stopped spinning in any noticeable way. The ground beneath your boots would hold the memory of a warmer past, when the planet still circled a star and felt real daylight touch its surface. That memory is frozen into the crust now, sealed under ice that has not moved in ages. The open question remains simple, even if the answer is not. Is a rogue planet's surface a dead shell over a colder core, or the visible edge of something still faintly alive underneath? The evidence stays thin, pieced together from theory, physics, and comparisons to worlds we can actually study. For now, the surface stays what it has always been to us, a quiet, frozen unknown, drifting through the dark, waiting for warmth that may or may not still be there. If you could stand on the frozen crust of a rogue planet, your boots would rest on something harder than any ice you have touched before. The surface would be brittle, cold enough to crack under its own weight. But beneath that crust, something else might be waiting, something warmer, something that moves. We already know this pattern from worlds inside our own solar system. Moons like Europa and Enceladus show cracked, icy shells on the outside, yet scientists believe liquid oceans hide underneath. The heat does not come from a sun, it comes from within or from the gravitational squeeze of a nearby planet. A rogue world, drifting with no star at all, would need to find its warmth somewhere else entirely. One place to look is the core. Rocky planets carry radioactive elements left over from their formation, elements like uranium and thorium that decay slowly over billions of years. That decay releases heat, the same kind of heat that keeps Earth's interior molten today. On a rogue planet, this slow radioactive glow might be the only fire left burning. It would not warm the surface, it would not touch the frozen crust above, but deep down, it might keep something liquid. Some researchers wonder whether that heat could be enough to sustain a hidden ocean, sealed under miles of ice, sealed off from the black sky above. If you drilled down through that crust, the temperature would rise slowly at first, then more steadily the deeper you went. Somewhere down there, ice might give way to water, dark water, under enormous pressure, moving in currents that no sunlight has ever touched. The idea gets more interesting when a rogue planet has kept a moon. A planet traveling alone through the dark might still have companions traveling with it, bound by gravity long after the star that once held them both has been left behind. If a moon orbits close enough, and if that orbit is not perfectly round, the planet and moon can pull and stretch each other with every pass. This stretching, called tidal heating, warms the moon's interior the way squeezing a rubber ball again and again warms your hand. It is one explanation for why Europa's ocean might still be liquid, even though sunlight there is faint and distant. For a rogue planet's moon, this could matter even more. With no starlight at all, tidal heating might be the only heat source that counts. A contrasting view holds that without a nearby star to anchor stable orbits, moons around rogue planets may be rare, or their orbits may be unstable, decaying inward, or drifting away over millions of years. If that is true, this hidden warmth would not last forever. The ocean, if it ever existed, might eventually freeze solid as the tidal squeezing fades. There is also the question of the atmosphere thickening into something unexpected. Gases that would normally stay airborne near a warm star can freeze into solid layers on a rogue world's surface, coating the ground in something like snow made of nitrogen or frozen CO2 under that strange frozen blanket. Some scientists propose the ground itself could trap a small amount of heat, insulating what lies beneath the way a blanket of snow insulates soil on Earth in deep winter. Others argue the effect would be too small to matter, swallowed by the relentless cold of interstellar space, where temperatures can fall to only a few degrees above absolute zero. If you pressed your hand against that surface, you would feel nothing living in it, only stillness, so deep it would seem to swallow sound itself. And yet, kilometers below your feet, if these theories hold, there might be motion. Water sliding past rock, chemical reactions unfolding in total darkness, the way they do near volcanic vents on the ocean floor of Earth, where no sunlight reaches and life still finds a way to feed on chemistry alone. This process, called chemosynthesis, does not need starlight. It only needs heat and minerals and time. Nobody has confirmed a rogue planet ocean. No probe has drilled through that crust, and no telescope can see that deep. Everything here rests on models, on comparisons to icy moons we have actually measured, and on careful extrapolation into places we cannot yet reach. Some researchers find the comparison compelling. Others caution that a lone planet with no tidal partner and no radioactive core large enough to sustain the heat might simply freeze through all the way down, leaving nothing but silence in every layer. The truth may be different for every rogue world. Some might be frozen through completely, solid to the core, offering nothing but stillness in every direction. Others might carry a secret ocean, warm and dark, moving quietly beneath a shell of ice, hidden from every star in the sky above it. For now, if you stood on the ice of a rogue planet, you would feel no rhythm at all in the sky above you. There would be no sunrise, no sunset, no slow turning of seasons that mark the passing of a year. And yet, deep below your feet, something might still be moving in a slow and patient cycle of its own. Every world with a molten core has a kind of heartbeat. Radioactive elements buried in the rock decay, releasing heat in a process that can last for billions of years. Tidal forces, if a moon is nearby, squeeze and flex a planet's interior, warming it from within. These are not the fast rhythms of day and night. They are the slow, grinding cycles of geology, and they may be the only pulse a rogue planet has left. Some researchers wonder if that pulse is enough to sustain something more on Earth. We have found life clustered around volcanic vents on the ocean floor, far from any sunlight, feeding on chemical energy instead of light. This process, called chemosynthesis, lets simple organisms build energy from chemical reactions rather than from starlight. If a rogue planet keeps a liquid ocean beneath a shell of ice, warmed by its own slow decaying heart, a similar process might be possible there too. The idea stays speculative. No one has found life on a rogue planet, or even direct evidence of an ocean beneath one. What we have is a pattern borrowed from closer to home, applied to a colder and more distant kind of world. If such a cycle exists, it would move at a pace almost impossible to imagine. A planet's internal heat fades slowly over spans of time longer than human civilization. There would be no seasons to mark decades or centuries. Instead, the only change might be a barely perceptible cooling, stretched across millions of years as the core radiates its last warmth into the dark. Tidal heating offers a different kind of cycle, one that repeats more often. If a rogue planet still holds a moon, the constant gravitational pull between the two bodies can flex and squeeze the planet's interior again and again. This is the same process that keeps some moons of Jupiter geologically active, despite their distance from the Sun. A rogue planet with a moon might experience a version of this squeezing on a steady repeating schedule, even while its outer surface remains locked in permanent cold. Your body, standing on such a world, would feel none of this. The ice above would seem still and silent, the sky black and empty of any warming light. Whatever cycle exists would be happening far below, in a place your senses could never reach. Some scientists propose that a planet's size plays a role in how long its inner cycle can last. A larger, Jupiter-sized rogue world holds more heat from its formation and takes longer to cool. It may also hold a thicker atmosphere, insulating the heat trapped inside for a longer stretch of time. A smaller, rocky world might lose its inner warmth faster, its cycle ending sooner, its chance for any subsurface warmth fading earlier into the dark. There is another rhythm to consider, one measured not in heat but in motion. A rogue planet does not sit still. It drifts through the space between stars on a long, slow path that can stretch across millions of years. This drifting is its own kind of cycle, patient and directionless, carrying the planet closer to some star systems and farther from others over unimaginable stretches of time. If life exists deep inside such a world, it would ride along on this journey, entirely unaware of it, sealed away from the passing galaxy above. The competing view is quieter, more cautious. Perhaps radioactive heat and tidal flexing are not enough. Not without the steady input of a star's energy. Perhaps any subsurface ocean would eventually freeze solid, its chemical cycles slowing until nothing moves at all. This view does not deny the possibility of a cycle. It simply doubts that the cycle could sustain warmth or life for long enough to matter. No telescope has settled this question, and none may for a long while yet. Rogue planets are too dark, too distant, too well hidden in the black to study closely. What we have instead are patterns pulled from other worlds, other oceans, other kinds of heat, stitched together into a picture of what might be happening in the deep dark of a planet with no sun. If you could listen closely enough, past the ice and past the silence, you might hear the planet's own version of a slow, uneven breath, a cycle without sunlight to mark its time. A rhythm that may be carrying something alive, or may be carrying nothing at all, patient and unwitnessed in the endless dark between the stars. Picture a young solar system not long after its birth. It looks nothing like the calm, orderly place we imagine when we picture planets circling a sun. It is crowded, restless, and full of half-finished worlds, still jostling for room. Your body, if it could somehow drift through that early chaos, would feel the pull of many masses at once, tugging you first one way, then another, with no single gravity you could trust to hold steady. In these young systems, planets do not always find a peaceful orbit right away. Many form close together, sometimes only a short distance apart by planetary standards. Their gravity reaches out and touches its neighbors constantly. Over time, some of these worlds settle into stable paths, the way our own 8 planets eventually did. Others do not settle at all. One leading idea for how a planet becomes a wanderer starts right here, in this crowded newborn system. When 2 large planets pass close to each other, their gravity can interact in ways that fling one of them onto a completely new path. Sometimes that new path leads outward, away from the star, faster and faster, until the planet simply cannot fall back. It leaves, not violently, in the way we might picture an explosion, but through a slow mathematical process of energy being passed from one body to another, until one of them has enough to escape entirely. Astronomers call this process ejection, though the word makes it sound more dramatic than it might actually be. It could take place over a single close pass, or it could unfold gradually, over many orbits, as a planet's path grows wider and more stretched with each encounter. If you stood on such a planet during this stage, you might not even notice at first that anything unusual had happened. The star would simply grow smaller in the sky, orbit after orbit, until one day it stopped looking like a sun at all and became just another point of light. We know giant planets like Jupiter can move other bodies through gravity alone, because we see this kind of interaction happening in our own solar system today, on a much smaller scale. Our solar system likely rearranged itself somewhat early on, before things quieted into the pattern we know now. Some scientists think one or more planets might have formed in our own system and never made it to a stable orbit at all. If that happened, we would have no way of finding them now. They would already be gone, drifting somewhere far beyond the light of our sun. This is one of the quiet, unresolved parts of the story. We cannot look back in time and watch our own solar system's early years unfold. We can only study systems being born right now, in distant clouds of gas and dust, and try to guess what our own history might have looked like. Some of those young systems show signs of disruption, of planets that seem to be on their way out already, still glowing faintly with the heat of their formation. Whether they will actually escape, or eventually settle down, remains an open question for each one. There is a competing idea worth sitting with too. Not every rogue planet may have started inside a solar system at all. Some may have formed on their own, directly from a collapsing cloud of gas, never orbiting any star to begin with. If that is true, then the population of drifting worlds may be a mix of two very different histories, some cast out from crowded young systems, and some born already alone, with no star to lose. From the outside, once they are cold and drifting, we may have no way to tell which kind we are looking at. What we do know is that gravitational nudges of this kind are common enough in young systems that ejection seems like a natural and expected outcome of planet formation, not a rare accident. If that is right, then every star that ever formed planets may have also flung a few of them away, quietly over its early history. The number of orphaned worlds produced this way across the whole history of the galaxy is still only an estimate, built from models and educated guesses rather than a direct count. If you could watch one of these worlds during its final moments near its birth star, you would see no drama, no flash of light, no sound at all in the vacuum of space. Just a long, slow curve bending farther and farther outward until the star it once called home became indistinguishable from all the other faint points scattered across the dark. Picture a planet that never had a star to call home. Not one that was pushed out of a crowded system, not one that was flung away by a close pass with another world. This is a planet that formed alone in the cold space between stars, the way a star itself might form, but without enough mass to ever ignite. If you drifted near a world like this, you would find no memory of daylight in its atmosphere, no old warmth left over from a sun it once knew, because it never had one to begin with. Some researchers call these objects free-floating planets, and they may form the same way a star does, from a collapsing cloud of gas and dust that never gathers quite enough material to start burning. A star needs a certain mass to trigger nuclear fusion, the process that lights every sun in the sky. A cloud that falls just short of that threshold collapses into something smaller and colder. It becomes a body with planet-like mass, but with no star ever forming beside it. It never orbits anything. It never belonged to a system at all. This idea sits at the far edge of what we understand about how planets are made. Most planets, as far as we know, form in the swirling disk of leftover material around a young star, the way Earth formed around our own sun billions of years ago. But telescopes studying star-forming clouds, like the Orion Nebula, have found faint, isolated objects with masses close to that of Jupiter, just floating in open space, far from any star. Some of these may be failed stars, called brown dwarfs, too small to ignite fusion. Others may be true planets, born the same lonely way. The line between the two categories is still blurry, and astronomers do not fully agree on where to draw it. If one of these worlds exists at the low end of the mass scale, it could be a record holder in its own right, perhaps the smallest object ever to form in isolation, unattached to any star from the very beginning. Some estimates suggest such objects could have masses only a few times that of Jupiter, sitting right at the boundary of what we would even call a planet. Your eyes, standing on its surface, would find no sun anywhere in the sky, not even a faint one. Every point of light above you would belong to some other system, too far away to warm you. The extremes here are not just in size. Some of these starless worlds may be astonishingly old, drifting since the earliest years of the galaxy, older than most of the stars we can see tonight. Without a star's gravity to hold them on a fixed path, they simply continue moving, carried by whatever momentum they had when they formed. There is no orbit to complete, no year to mark, no season to notice. Time, on a world like this, would not be measured by circling anything. It would only be measured by distance covered, drifting through the dark for spans of time that are difficult to picture. One competing idea suggests that some of these free-floating worlds may not have formed alone at all. Instead, they might be planets ejected from young systems, so early and so violently that no trace of that system remains attached to them. No leftover disk, no companion moons, nothing to hint at their origin. Under this view, a starless world found drifting through a stellar nursery might simply be a normal planet that lost its home before astronomers ever caught sight of it. Telling these two origins apart, one born free and one cast out, is one of the open questions in this field. The evidence so far is not enough to say which explanation fits any single object we have found. If you stood on the surface of a planet like this, whichever way it came to be, your body would feel a cold that has never once been broken by starlight. There would be no dawn to wait for, no gradual reappearance of warmth after a long night. The darkness around you would not lift, because it was never going to lift in the first place. Any warmth beneath your feet would come only from the slow decay of elements inside the planet itself, a quiet furnace with no relationship to any sun. We do not yet know how common these truly starless worlds might be, whether they are rare oddities or a hidden population as large as the stars themselves. What we do know is that somewhere out there, cold and unclaimed, a handful of planets may have never once felt the light of a sun, not for a single moment since they formed. It is a strange kind of extreme to hold in mind, a world defined entirely by something it has never had. Picture yourself holding a telescope pointed at a patch of sky with nothing bright in it, no star, no glow, just black space, dusted faintly with distant points of light. Somewhere in that blackness, astronomers believe a planet the size of Jupiter might be drifting, cold and dark, giving off almost no light at all. Finding it would be like trying to see a piece of coal floating in a night that has no floor and no ceiling. This is the quiet puzzle at the center of rogue planet science. These worlds do not shine. They do not reflect starlight the way planets in a solar system do, because there is no nearby star to reflect. Whatever warmth they carry comes from deep inside, a faint leftover heat from their formation, seeping out into space as a dim glow you could only see in infrared light, the kind of light that carries heat instead of brightness. Even that glow is impossibly faint across the distances involved. If you stood beside such a telescope and looked through the eyepiece, you would see nothing where the planet was. You would need a machine built to sense heat instead of light, and even then, only the warmest, youngest rogue worlds leave any trace at all. One method scientists use is called direct imaging, catching that whisper of infrared heat with specialized telescopes tuned to wavelengths our eyes cannot use. This works best on the youngest rogue planets, the ones freshly formed or freshly cast out from their birth systems, still glowing faintly warm from their own creation. Older rogue worlds, the ones that have drifted for millions or billions of years, have cooled far past what these instruments can easily detect. This is one of the open puzzles researchers sit with. The population of rogue planets we can actually see may be nothing like the full population that exists. The cold, ancient ones might vastly outnumber the young glowing ones we can spot, hidden simply because they have had more time to lose their warmth. Another approach uses a strange trick of gravity itself. Sometimes a hidden object passes directly between us and a distant background star. That hidden object bends the star's light around itself for a brief moment, acting like a lens made of gravity rather than glass. The background star flickers brighter for a few hours or days, then fades back to normal, and that flicker is the only clue a rogue planet ever passed by. Astronomers call this microlensing, and it offers something remarkable, a way to detect an object that gives off no light of its own through the pure bending of space around its mass. But it comes with a trade. Each event happens once. It cannot be repeated, cannot be double-checked by looking again. The object has already moved on into the dark, and researchers are left studying a single, fleeting signature of light. If you were floating in the space between stars, watching one of these events unfold from a great distance, you would see only the faintest twitch in a distant point of light, the kind of subtle change a human eye could never notice unaided. It would take incredibly sensitive instruments, watching millions of stars every single night, patiently waiting for one of them to flicker in just the right way. Some researchers describe this work as searching for a shadow, crossing a shadow so faint that most nights bring nothing at all. There is a quiet beauty in how indirect all of this evidence is. No photograph exists of a rogue planet the way a photograph exists of a planet orbiting a nearby star. What exists instead is a collection of brief events, warm smudges in infrared images, and careful statistics built from thousands of hours of watching. Each rogue planet candidate is less like a snapshot and more like a fingerprint left in dust, a trace of something that was there and then continued on its way through the dark. Some scientists wonder whether upcoming space telescopes, built with wider fields of view and more sensitive detectors, will finally begin to reveal how common these worlds truly are. Others caution that even the best instruments may only ever catch the closest, largest, or youngest rogue planets, leaving smaller and older ones forever, just beyond reach. The disagreement is not about whether rogue planets exist. The evidence for that is already strong. The disagreement is about how many are truly out there, and how much of that population might always remain invisible to us. For now, each detection feels less like an answer and more like a single quiet note in a much longer, unfinished song. You are left, as they are, listening for the next flicker in the dark, and wondering how much of that darkness is simply waiting to be noticed. Picture a night in the mountains, at an old telescope dome with a slow turning roof. Astronomers waited there for years, watching one small patch of sky night after night. They were not looking for light, they were looking for a bend in it. If you sat beside them in that cold dome, you would feel the quiet hum of machines and the patience of people doing very slow work. Finding a rogue planet, a world with no star of its own, cannot be done by looking for its glow. It gives off almost none. Instead, astronomers had to wait for something rarer. They had to wait for a rogue planet to pass by pure chance in front of a distant star. This method is called gravitational microlensing, and the idea behind it comes from Einstein's understanding of gravity. Mass bends space around it, the way a heavy ball bends a stretched sheet of rubber. Light traveling near that mass follows the bend. When a planet drifts directly between us and a background star, its gravity acts like a lens. For a short time, the star's light bends and brightens, then fades back to normal as the planet moves on. The tricky part is scale. A star passing in front of another star creates a lensing event that might last weeks. A planet is much smaller and lighter, so its lensing event might last only a day, sometimes only a few hours. Astronomers had to watch millions of stars at once, hoping to catch a flicker that most people would dismiss as noise. You can imagine the exhaustion of that kind of watching, the eyes straining, the long stretches when nothing happens at all. Projects with names like OGLE and MOA, ground-based surveys built for exactly this kind of search, scanned the crowded star fields toward the center of our galaxy. That direction holds the densest thicket of stars, which means more chances for something small and dark to cross in front of one of them. Teams in Chile, New Zealand, and Poland pointed their telescopes there night after night, comparing images, watching brightness curves rise and fall on their screens. In the early 2000s and into the 2010s, some of these brightening events looked strange. They were too short, too sharp, to match the signature of a star or even a planet still orbiting one. Some researchers proposed these signals came from free-floating planets, unbound to any star, drifting through the galaxy alone. Other astronomers were more cautious. A short lensing event could also come from a planet on a very wide, very distant orbit, around a faint star too dim to detect. The data alone could not always tell the difference. That uncertainty has never fully gone away. If you had watched one of these brightening curves appear on a screen in real time, you would have felt the strange thrill of catching something that might vanish and never repeat. Microlensing events do not return. The planet and the background star are both moving through the galaxy, and the alignment that caused the brightening will never happen again in exactly the same way. Each detection is a single, unrepeatable clue. There is no second look, no chance to point a bigger telescope at the same event later and confirm it directly. Astronomers have had to build their case out of statistics, out of many short flickers gathered over years, rather than one clean, certain sighting. By combining thousands of these events, researchers began to estimate how common rogue planets might be. Some studies suggested there could be more free-floating planets in our galaxy than there are stars. Though this estimate carries real uncertainty and remains debated, other analyses suggest the numbers are lower, or that many of the short events come from planets in very distant orbits rather than truly unbound worlds. The honest picture is that nobody has a final count. What microlensing gave astronomers was not a census, but a hint, a flicker of statistical evidence pointing toward a population of worlds that might vastly outnumber the stars they used to circle. Mistakes happened along the way. Some early candidate events turned out to be ordinary variable stars, or instrument errors, or the passage of asteroids much closer to home. Each false alarm forced astronomers to refine their methods, to build better models of what a true planetary lensing signal should look like. The work moved slowly, correction by correction, doubt by doubt. If you stood in that dome tonight, watching the same brightness curve scroll across a screen, you would feel the particular patience this science demands. There is no roar of discovery here, no dramatic reveal. There is only a faint dip and rise in starlight, gone before you can look twice, and the quiet work of turning that flicker into evidence for worlds that have no sun at all. picture a cloud of gas and dust, glowing faintly in shades of rust and violet, light years wide. This is a star-forming cloud, a nursery where thousands of stars are born at once. If you drifted through it, your body would feel nothing at all, because the cloud is thinner than the best vacuum we can make on Earth. And yet inside these clouds, astronomers have found something strange. Along with the newborn stars, there are objects that look like planets, drifting completely alone, with no star to call their own. This surprised almost everyone who first saw the data. The assumption had always been simple. Planets need a star to form around. A young sun gathers gas and dust into a spinning disk, and planets grow inside that disk, like pearls forming in layers. That picture still holds true most of the time, but surveys of nearby star-forming regions, like the Orion Nebula and other stellar nurseries, turned up objects with planet-like masses that were not orbiting anything. They were simply there, floating between the stars, as if they had formed with no star at all. One idea is that some of these objects grew the same way stars do. A small clump of gas in the cloud can collapse under its own gravity, pulling itself into a dense, spinning ball. Usually this process makes a star, but sometimes the clump is too small to ignite nuclear fusion, the process that powers starlight. Instead of becoming a star, it becomes something in between, a shape with planet-like mass, but a star-like birth. Researchers call these objects free-floating planetary mass objects, and their existence still puzzles the people who study them. A competing idea says something more familiar happened. These objects may have formed the ordinary way, inside a disk around a young star, and then been thrown out early by the same chaotic gravity that ejects rogue planets from older systems. In a crowded, newborn cluster, stars pass close to one another. Their gravity tugs and pulls at any planets nearby. A planet still forming, still soft and loosely held together, could be flung free before it ever finishes growing. If this is true, then some of what looks like a lonely, almost star is actually a very young rogue planet, cast out before its own system even settled down. The honest answer is that no one fully knows which explanation fits which object. Telescopes can measure brightness and estimate mass, but they cannot watch the birth itself. If you stood on one of these drifting bodies, near a stellar nursery glowing red and gold in the distance, you would not be able to tell by sight alone whether you were standing on a failed star or an exiled planet. The light around you would look almost the same either way, faint and colored by the cloud's own glow, rather than sunlight, because there would be no sun close enough to light your ground. What makes this stranger still is the sheer number of these objects. Some surveys suggest that free-floating planetary mass bodies may be common in star-forming regions, almost as common as the stars they drift beside. If that estimate holds up, it means our galaxy's youngest neighborhoods are seeding dark, sunless worlds by the thousands, long before any of those worlds could have had a star to lose. It also means the line between planet and failed star, a line that once seemed obvious, is far blurrier than most people assume. Some researchers wonder if these young drifting worlds ever settle down. A few might eventually be captured by a passing star, pulled into an orbit and given a sun after all, though this kind of capture would be rare and slow, happening over spans of time longer than a human mind can easily hold. Others may drift for the rest of their existence, exactly as they began, alone in the dark, cooling slowly, never gathering the warmth of starlight at all. If you imagine floating near one of these newborn nomads, your skin would feel the cold of true isolation, colder than any night on Earth, with no dawn ever coming to change it. The nebulous soft glow might color the sky in faint reds and purples, but it would never rise or set because there is no orbit here to create a day. It would simply hang there, distant and dim, a reminder that this world formed with no promise of a star at all, whether it began as a planet exiled too soon or as a star that never quite caught fire, remains an open question the cloud itself is not yet ready to answer. Picture a body drifting slowly through the space between. Two definitions, unable to settle into either one. That is what a rogue world does, in a sense, in the minds of the people who study it. If you stood on its frozen surface, you would not care what name it carried, but the name matters to the scientists trying to understand what you are standing on. A planet, by one common definition, is a body that orbits a star and has cleared its neighborhood of debris. A rogue world orbits nothing. It has no star to circle, no center to hold it in place. So some researchers ask a quiet, patient question. Is it still a planet at all, or does it belong to some other category we have not fully named yet? One idea is that mass should decide the matter, not orbit. Under this view, if a body is round, if it formed the way planets form, and if it sits below the weight needed to ignite nuclear fusion in its core, it counts as a planet regardless of what it circles. This is the same rough line that separates a planet from a star. Cross that mass threshold and hydrogen begins to fuse, and you have made a small, dim star instead. Stay below it, and you remain something else, something that only shines by reflection or by its own leftover heat. But other researchers lean toward a different marker. They point to brown dwarfs, the strange dim bodies that sit between planets and stars, too small to fully ignite, but too massive to be called ordinary planets. Some rogue worlds may have formed the exact same way brown dwarfs do, by collapsing directly out of a cloud of gas, never orbiting anything, never getting flung from a family of planets at all. If that is true, then calling every rogue world a planet may blur two very different kinds of birth into one tidy word. The boundary between a very large rogue planet and a very small brown dwarf remains soft, argued over, unresolved. You can imagine two of these worlds side by side, similar in size, similar in temperature, drifting the same kind of silent path through the dark. One formed the ordinary way, circling a young sun until a gravitational shove sent it outward into permanent exile. The other formed alone from the start, condensing out of cold gas the way a star does, but stopping short of catching fire. From the outside, floating near either one, your eyes would see almost the same thing, a dark sphere, faintly warm at its core, silent against a field of unfamiliar stars. The difference is written only in its past, not in its present shape. This connects to a larger pattern astronomers keep noticing. The universe rarely hands out clean categories. Planets blur into brown dwarfs. Brown dwarfs blur into small stars. Moons blur into dwarf planets. Rogue worlds sit at one more soft edge in a long line of soft edges, reminding us that our labels are drawn after the fact, stretched over a system that formed without asking our permission. The sky does not sort itself into boxes for our convenience. Some scientists suggest we should stop trying to force a single word onto every wandering body, and instead track its history whenever we can. Did it form near a star and get thrown out later? Did it form alone from a collapsing pocket of gas, with no star involved at all? The answer changes what the object can tell us, even if its surface looks the same either way. A world ejected from a crowded young system may carry chemical fingerprints from that system, faint traces baked into its atmosphere or its ices, A world born alone would carry no such fingerprints, only the raw material of the cloud it condensed from. Telling these two histories apart from a distance, using only the faint light or gravitational tug a rogue world offers us, remains genuinely difficult. Our instruments are good at finding motion and mass. They are far less good at reading a biography. For now, many rogue worlds sit in a kind of scientific waiting room, tentatively called planets, while researchers gather enough evidence to say more. If you drifted near one tonight, none of this debate would announce itself to you. There would be no label glowing on its surface, no signpost marking which family it came from. There would only be the dark, the cold, and the quiet shape of a world that does not know, or perhaps does not need to know, what we decide to call it. The universe built it, one way or another. We are still working out which. Picture a world moving through the dark, carrying no memory of where it started. If you stood on its frozen crust, you would feel nothing that told you this was a journey. No wind marks the miles. No light logs the years. And yet the world beneath your feet is always in motion, crossing distances too large for a human life to measure. A rogue planet does not orbit anything. Instead, it drifts through the space between stars, pulled only by the faint gravity of whatever it happens to pass. Over 1 million years, it might cross a distance of several light years. That sounds slow, and in some ways it is. But against the size of a galaxy, it is a steady, patient wandering, one that never stops and never repeats. Astronomers who model these paths describe them as long, looping drifts, shaped gently by the pull of nearby star clusters and the greater pull of the galaxy's spinning disk. The planet does not choose its direction. It simply responds to whatever mass lies nearby. The way a leaf on a pond drifts toward the deepest part of the current. Over enough time, a rogue world might drift near a young star system, then slip past it, tugged briefly and released again. Some researchers wonder whether these near passes could occasionally end differently, with a planet being pulled into a loose new orbit, caught by a star it never belonged to. If you were standing on such a world during a pass like that, you might notice the sky brightening for the first time in your journey, one star growing slightly larger before fading again into the crowd. Over cosmic time, the galaxy itself is not static either. Spiral arms rotate, star clusters drift apart, and even the path that rogue planets follow shift as the mass around them changes. A planet ejected during the early history of the galaxy would have moved through a very different sky than one ejected more recently, because the stars themselves have shifted position over billions of years. The universe is not a fixed backdrop. It behaves more like a very slow tide, shaping the paths of everything caught inside it, including the loneliest wandering worlds. Some scientists think many rogue planets settle into orbits loosely bound to the galaxy's center, tracing slow circles that take hundreds of millions of years to complete. This is different from orbiting a star. It is closer to being swept along in a much larger current, one shaped by the combined gravity of billions of stars, rather than a single sun. Under this idea, a rogue world's path could remain surprisingly stable for long stretches, drifting gently rather than tumbling chaotically. A competing view suggests that many rogue planets follow much more erratic paths, shaped by chance encounters with passing stars or dense clouds of gas. In this picture, a rogue world's route could shift unpredictably, bending one way after a distant gravitational nudge, then another way after the next. The truth may depend on the planet's original ejection speed and direction. details we usually cannot know, since the planet appears to us only as a single point of missing light. If you tried to imagine standing on the surface through all of this, the changes would be almost impossible to notice in a human lifetime. Your breath, if you could take one, would form no clouds, because there would likely be no thick atmosphere to hold moisture. The temperature would stay locked near the surface's frozen baseline, drifting only slightly as the interior heat below shifts with time. Any change to your sky would happen so slowly that centuries might pass before a single star noticeably moved position. And yet, over enough time, change is the only certainty. Stars die and form. Clusters dissolve. Galaxies merge and reshape their populations of drifting bodies. Somewhere, within all of that slow reshuffling, rogue planets continue their unclaimed paths, some drifting toward brighter regions, some drifting toward emptier ones. Whether most of them stay lost forever, or whether many eventually find a new gravitational home, remains an open question. The clues are faint, drawn mostly from computer models, rather than direct observation, since we still cannot easily track a single rogue world's path across galactic time. If you stood there long enough, you might come to feel that stillness and motion are the same thing on a world like this. Nothing around you changes quickly, yet everything is moving, carried by forces too large to see and too slow to feel. The dark space you crossed tonight might not look any different from the dark space you crossed 1,000 years ago. But somewhere in that vast, patient drift, the galaxy is quietly rearranging the paths of worlds, like this, one immeasurable step at a time. Light is the one thing a rogue planet almost never gives you. If you stood on the frozen crust of one of these worlds, you would wait a long time for anything at all to catch your eye. No sunrise, no glow on the horizon, just starlight, thin and scattered, falling from every direction at once, like dust settling on dark water. That absence of light is exactly why counting these worlds is so hard. A normal planet gives itself away by blocking or reflecting the light at its star. A rogue planet has no star to block. It drifts through the dark, carrying only the faint warmth left over from its own birth, a glow too dim for almost any telescope to catch directly. So, the question of how many are out there becomes a question about shadows we cannot quite see, only infer. One method astronomers use is called gravitational microlensing, a phenomenon where the gravity of an unseen object bends and brightens the light of a distant star passing behind it. For a few hours or days, a star flickers brighter than it should, and then fades back to normal. That flicker is the fingerprint of something massive and dark crossing in front of it. Some of those flickers last only a very short time, shorter than the ones caused by stars, and researchers believe many of these brief events come from planet-sized objects with no star of their own. Counting flickers is not the same as counting planets, though. Microlensing events are rare, and they depend on a chance alignment between the hidden object, a distant star, and Earth. For every rogue planet that happens to cross paths with starlight we are watching, there may be many more that never do. Some researchers who model these numbers suggest that rogue planets could outnumber the stars in our galaxy, perhaps by a significant margin. Others caution that the current data is thin, built from a small number of confirmed detections, and that the true count could be far lower than these early estimates suggest. The honest answer, right now, is that no one knows for certain. If light from these worlds is faint, color becomes a strange thing to imagine too. A star gives a planet its palette, the blue of scattered sky, the gold of sunset, the red of iron dust lit from above. Take the star away, and a rogue planet's surface would likely settle into deep greys and blacks, broken only by starlight glinting faintly off frost or ice. If the planet still holds a thin atmosphere, gases could freeze out entirely, falling like fine snow onto the ground below. Some scientists picture this frost forming quiet, pale sheets, like the surface of Pluto, but colder, dimmer, and lit by no sun at all. There is another kind of light to think about, though, one that does not come from outside the planet. Some rogue worlds may still glow faintly with their own inner heat, a dull red seeping up from deep below the crust. This heat comes from leftover formation energy and the slow decay of radioactive elements inside the core, the same processes that keep Earth's interior molten today on a large rogue planet, especially one closer to the mass of Jupiter. This internal glow could linger for billions of years. If you pressed your hand to the ground on such a world, it might feel warm, even while the air above you sits near absolute zero, the coldest possible temperature. Some researchers wonder whether this hidden warmth might be enough to keep something interesting happening far below the ice, even without a hint of daylight above. Others argue that without a star, any warmth radiating from below would simply bleed away into space over time, leaving even the interior cold and still. Both ideas remain open, resting on models rather than direct observation, because no telescope has ever mapped the deep structure of a wandering world. What we are left with then is starlight bending around invisible shapes, faint thermal glows too dim to properly measure, and statistical guesses stretched across a galaxy we have barely begun to search. Each flicker, recorded by a microlensing survey, might represent one planet, or a hint of thousands more we have not yet seen. If you tried to count them yourself, standing on such a world, you would find no glow to guide your eye, no horizon lit by a rising sun. You would only feel the quiet hum of your own breathing, and see, somewhere far off, one point of light among thousands, giving away nothing about how many others like it drift silently nearby. If you stood on a rogue planet, you would hear nothing at all. Space carries no air, and without air, there is no sound the way we know it here on Earth. Your own breathing, your own heartbeat, would be the only sound left to you, small and steady in a silence that has no edges. But the planet itself is not silent, not in the way we might think. Deep inside its rock and metal body, there is still motion, heat left over from its violent birth, and the slow decay of radioactive elements in its core keep the interior restless. That restlessness could cause tremors, the same way heat inside the Earth causes earthquakes. If you pressed a sensor against the ground, you might catch the low groan of a world settling into itself, a sound with nowhere to go and no one to hear it. Scientists cannot record this directly, of course. No spacecraft has ever landed on a confirmed rogue planet, but researchers can study something close to it. They have placed seismometers, tools that sense ground vibration, on our own moon, and on Mars. Those instruments picked up faint rumbles, quakes far gentler than Earth's, moving through frozen ancient rock. A rogue planet, older and colder still, might hum with something even quieter. One idea is that its tremors would be sparse and slow, echoes of a world that finished most of its shaking long ago. There is another kind of sound worth imagining, one that comes not from the ground, but from the space the planet moves through. Even in the thin nothing between stars, there are charged particles drifting and magnetic fields bending around them. Instruments on spacecraft can catch these fields flexing and turn that data into sound, the way NASA has done with recordings from Saturn's rings or the solar wind streaming off our sun. Those recordings sound like whistles, static, low tones rising and falling, though none of it is sound in the true sense. It is vibration translated into something our ears can hold. If a rogue planet carries its own magnetic field, shaped by a molten or partly molten core, it might create a similar kind of hidden song, one that only an instrument could ever notice. Whether rogue planets keep strong magnetic fields at all remains an open question. A. Planets' magnetism often depends on a churning liquid core, kept moving by heat and by the pull of a nearby star, or a large moon cut loose from a star. Some of that churning motion might slow down over time. Other researchers argue the core's heat alone, especially in a large, Jupiter-sized world, could keep the dynamo running for billions of years. No one has measured a rogue planet's magnetic field directly, so both possibilities remain open, waiting on evidence we do not yet have. If ice covers such a world, another kind of sound might rise. On Europa and Enceladus, moons in our own solar system with icy shells over hidden oceans, scientists suspect the ice cracks and groans as it flexes under strain. Recordings of Antarctic sea ice on Earth offer some sense of what that might resemble. High creaks and low booms carried through frozen water. A rogue planet with a buried ocean, kept warm by leftover heat far under its surface, might carry that same kind of slow, cracking voice, sealed away where no wind could ever carry it outward. You would feel none of this through your ears, standing there in an airless void, but you might feel it through your boots. Vibration can travel through solid ground and into a body standing on that ground, even when no air exists to carry a sound wave. A deep tremor might arrive as a shiver under your feet, quiet and patient, less like sound and more like memory. The planet moving slowly, the way it has for millions of years, unwitnessed by anyone at all. It is a strange kind of music, if we can call it that. A hum of heat trapped since the planet's birth, a whisper of a magnetic field. If one still turns inside the core, a groan of ice, sealed far below a surface that never sees light. All of it happening in true silence. Sound that never becomes sound, because there is nothing around the planet to carry it, only an instrument, pressed to the rock, could ever translate that motion into something we would recognize. We do not know for certain which of these sounds, if any, a real rogue planet would produce, or how loud, or how often. Every idea rests on comparison, on what we have measured elsewhere and carried forward as a guess. The true acoustic life of a drifting world, cut loose from any star, stays just past our reach. Somewhere out there, a world may be humming to itself in the dark, and we have no way yet to listen. Picture yourself lying on your back on a rogue planet, looking straight up. There is no sun to squint against, no blue haze of daytime sky to hide anything from view. What you would see instead is a kind of math made visible, a sky built entirely from distance and light, with nothing nearby to compete for your attention. The first thing you would notice is how steady it all is. On Earth, our sky changes by the hour, the sun sliding, the moon shifting shape, clouds rearranging themselves without pattern. On a rogue world, drifting through the space between stars, the sky would barely move at all. The stars would hang fixed, or nearly fixed, shifting only as fast as the planet itself travels through the dark. That drift is slow, by any human measure, often just tens of kilometers per second, which sounds fast until you remember the distances involved. At that pace, crossing the gap between two star systems can take hundreds of thousands of years, sometimes millions. Your body, standing there, would feel no wind, no rotation, nothing but the cold and the quiet weight of your own presence in that stillness. The numbers behind starlight itself are part of what makes this sky honest in a way ours is not. Every point of light you would see left its star years ago, sometimes thousands of years ago, traveling at exactly one speed, the speed of light, about 300,000 kilometers every second distance, and time become the same measurement out there. A star, sitting 4 light years away, shows you a version of itself that is 4 years old. One sitting 1,000 light years away shows you the past 1,000 years deep. If you tried to pick out the star your planet once orbited, before whatever gravitational shove sent you drifting, you might not be able to. Some researchers who study rogue worlds suggest that without spectral clues, a chemical fingerprint in the planet's atmosphere or crust, there may be no way to trace it back. The parent star, if there ever was, one becomes just another unlabeled point among thousands. There is a strange elegance in how few objects would actually share your sky. Earth's night sky holds roughly a few thousand stars, visible to the naked eye, all bound by the thin blue filter of our own atmosphere and the glow of our own sun nearby. A rogue planet, drifting through true interstellar space, far from any star's light, would show a sky arguably cleaner and darker than anything a human being has ever stood beneath. No scattering, no glow on the horizon, nothing to dilute the black. The stars would look sharper, more numerous in places, the Milky Way's pale band stretching edge to edge, with nothing to compete against it. It would be, by any measure of contrast and clarity, a more perfect view of the universe than we get from home, and yet nothing in it would ever move fast enough to notice, and no warmth would ever reach you standing in it. Some of the math turns genuinely playful when you consider a rogue planet's chance of ever passing near another star. Interstellar space is vast, and stars themselves are small compared to the distances between them. Estimates suggest a wandering planet might go tens of millions of years between anything resembling a close pass. The odds of 2 objects meeting at random across such emptiness are close to nothing, which is part of why some scientists think rogue planets, once ejected, tend to stay lost. Others point out that over billions of years, the age of the galaxy itself, even tiny odds accumulate. A planet, with enough time, might eventually drift close enough to a star system to be nudged, captured, or reshaped by gravity again. Whether this actually happens with any regularity remains an open question, resting on probabilities too slow for any human observation to confirm directly. If you tried to calculate your own position out there, you would find the usual tools fail you. No day length to count, no orbit to time, no seasons to mark years. The only clock left would be the stars themselves, shifting with a patience too slow to notice across a single lifetime, moving instead across whole geological ages. Your body would feel that timelessness as much as the cold, a sense that time out there is measured not in days, but in the slow turning of the galaxy itself. The numbers behind a rogue planet's sky are simple: distance and light and gravity, but the picture they build is something almost impossible to picture from Earth. A perfect, silent geometry, drifting, unclaimed, and entirely alone. Picture yourself lying in an open field at night, far from any city light. You feel safe there, because the sky above you feels fixed and slow. The planets seem to hold their quiet places, circling the sun the way they always have. But that stillness is a kind of illusion built from very long timescales. Rogue planets remind us that solar systems are not calm rooms. They are crowded, shifting spaces, and sometimes something gets thrown out the door. This raises a quiet question worth sitting with. Could a rogue planet ever drift close to our own solar system? The honest answer is that it is possible, though the chances over any human lifetime are extremely small. Space is vast, and even a fast-moving rogue world would spend most of its long existence crossing empty distances between stars. Still, the math does not rule it out completely, and that is part of what makes the idea so quietly compelling. If a rogue planet did pass through our solar system, the outcome would depend heavily on its mass and its path. A small rocky wanderer might slip by unnoticed, its gravity too weak to disturb much of anything. A larger world, especially one with the mass of a gas giant, could tug at the orbits of comets in the distant, icy edges of our system. Some researchers wonder whether past visits like this, if they ever happened, might explain unusual orbital patterns we still cannot fully account for today. That idea remains speculative, but it is not dismissed outright. Your body standing on Earth during such a distant flyby would likely feel nothing at all. The scale of a solar system is so large that even a significant gravitational nudge to outer bodies would not shake the ground beneath your feet. The danger, if any existed, would unfold over thousands of years, in slow shifts of distant orbits, not in a single dramatic night. This is where the fragile balance of our own system becomes worth remembering. Earth sits in a narrow band of distance from the Sun, often called the habitable zone, where liquid water can exist on a surface. Move Earth only a little closer, and the heat would boil away our oceans. Move it a little farther, and the cold would lock them into ice. The thin atmosphere wrapped around our planet, only about 100 kilometers thick before it fades into space, holds in just enough warmth and blocks just enough radiation to let life persist. None of this is guaranteed by any law of physics. It is closer to a fortunate arrangement, refined slowly over billions of years. A passing rogue planet becomes interesting precisely because it has none of these gentle arrangements. It carries no habitable zone, no steady sun, no atmosphere shaped by careful balance. If it does have an atmosphere, it likely exists as a thin, frozen crust rather than a living sky. Some scientists propose that a rogue world with enough internal heat, generated by radioactive decay deep in its core, might sustain something warm underground, even without a sun. Others counter that without a steady source of outside energy, any such warmth would be modest and short-lived on a planetary timescale. The disagreement remains unresolved, and both views stay open. If you imagine standing on a rogue planet that has drifted near a star system like ours, even briefly, you would not feel the pull of gravity in any dramatic way. Your body would still stand upright, still breathe if the air allowed it, still feel the quiet solidity of ground beneath your boots. What would be missing is the sky's usual order. There would be no single dominant sun rising or setting, only a distant scatter of starlight, and perhaps briefly an unfamiliar bright point marking the star being passed. The deeper mystery is not really about danger. It is about how ordinary the movement of worlds might actually be, hidden from us by unimaginable timescales. Our sun, formed in a crowded stellar nursery alongside many siblings, and some of those young systems likely ejected planets of their own during the chaos of formation. It is not unreasonable to imagine that rogue worlds occasionally sweep past sun-like stars, simply as a matter of galactic traffic. Rare on human timescales, but common across cosmic ones. Whether one has ever passed near us, quietly unnoticed, sometime in Earth's 4.5 billion years of history, is something we may never know. The evidence would be faint, buried deep in the outer geometry of our solar system, rather than written anywhere we can easily read. For now, the fragile balance that lets life exist here remains intact, undisturbed, and delicately maintained by distance, chemistry, and time. Whether that balance has ever been quietly tested by something drifting through the dark is a question that stays open, patient, and unanswered above your head tonight. Picture a rogue planet drifting in the dark, and then picture something even smaller beside it, a moon, not orbiting a bright world lit by a sun, but circling a cold body that has no sun of its own. If you tried to imagine standing on that small moon, you would find no horizon glow, no distant star to mark up from down, just two dark shapes turning slowly around each other, alone. The question of rogue moons is one of the newer puzzles in this field, and it stays mostly unanswered. When a planet gets thrown out of its solar system by a close pass with another planet or a passing star, does it always travel alone? Or does it sometimes carry a companion with it, torn free at the same moment, bound to the planet by gravity even as both leave their star behind? Nobody has confirmed a moon around a rogue planet, but nothing in the physics rules it out. Think about how planets keep their moons in the first place. Gravity holds them close, a steady pull that keeps a smaller body locked in orbit around a larger one. That pull does not care whether a star is nearby. If a moon is already circling a planet, when that planet gets ejected from its system, the moon has a good chance of staying attached. The planet and the moon would simply leave together, a paired system slipping into the dark side by side. Some researchers who model these ejection events think this could happen fairly often, especially for planets that already had moons before things went wrong in their home system. Other researchers wonder if the same violent process that ejects a planet would also tend to strip its moons away. The kind of close gravitational encounter that flings a world out of its orbit is rough. It involves fast passes, sharp changes in speed, sudden tugs from massive neighbors. A moon orbiting loosely, far from its planet, might get pulled off during that chaos and lost separately, becoming its own small rogue body, drifting on a slightly different path through the same dark. If that happens, you would end up with two lonely wanderers instead of one paired system, moving apart from each other over millions of years, until neither remembers the other was ever close. This matters for more than just curiosity about orbits. If a rogue planet can keep a moon, that moon changes the story of what might survive on these worlds. A planet with no sun relies on its own leftover heat, held deep inside from its formation, to keep any liquid water from freezing solid. But a moon adds another source of warmth. As a moon and planet pull on each other with gravity, their shapes flex slightly over and over, and that flexing creates friction inside them. Scientists call this tidal heating, and it is the same process that keeps some of Jupiter's moons warm enough to hold liquid oceans under their icy shells. A rogue planet with a moon, or a rogue moon with its own planet-sized partner, could use this tidal squeezing to stay warmer than either body would manage alone. If you floated near such a pair, you would see something strange. Two dark shapes, neither one lit by any nearby star, pulling and flexing each other in total silence. No light would reveal the motion. You would only sense it, somehow, in the slow rhythm of gravity working on both bodies at once. It is a picture that is easy to imagine, but very hard to prove is really out there. The trouble is finding any of this. Rogue planets already emit almost no light, and detecting them takes patient, careful methods that catch only brief signs of their presence. A moon circling one of these planets would be smaller, darker, and even harder to notice than the planet itself. Our current tools were not built with this kind of detection in mind. Some astronomers think future instruments built to study rogue planets directly might eventually catch the faint gravitational signature of a companion moon. Others are less certain that any method available in the coming decades would be sensitive enough. So the question stays open, sitting quietly at the edge of what we understand about these wandering worlds. Do rogue planets ever keep their moons? Some moons become rogues on their own, drifting apart from the worlds they once circled. Nobody can say for certain yet. And that uncertainty is part of what makes this particular corner of the dark so interesting to imagine. Somewhere out there, perhaps, two shapes are turning slowly around each other, warmed only by their own gravity, unseen and unnamed. If you were floating beside them, you might feel that quiet tug of two lonely worlds, holding on to each other in the dark. Picture a telescope, cold and patient, waiting in the dark for a shadow to pass. That is one way we might find more rogue worlds in the coming decades. Right now, most of what we know comes from brief flickers called gravitational microlensing, where a hidden planet's gravity briefly bends the light of a distant star. The event lasts only hours or days. Then it is gone, and the planet keeps drifting, unseen again. If you stood on such a world during one of these rare alignments, you would feel nothing at all. The bending of light happening because of your presence would be invisible to you, a cosmic signature written for someone else's eyes, light years away. Future telescopes are being designed with rogue worlds in mind. Space-based observatories with wide fields of view could scan huge patches of sky continuously, catching these fleeting lensing events far more often than we do now. Some astronomers hope that within 20 years we might detect thousands of rogue planets instead of the handful we know today. Others caution that even with better instruments, the numbers may remain uncertain, because so much depends on assumptions about how planets form and how easily they get flung into the dark. The truth is, we are still building the tools to ask the question properly. Infrared detection offers another path forward. A rogue planet, even without a sun, still glows faintly with its own leftover heat, the warmth left over from its formation, slowly leaking into space. This glow is impossibly dim by the time it reaches us, a whisper competing against the roar of every star in the galaxy. But infrared telescopes, tuned to exactly the right wavelengths, might someday pick out that whisper. If you held out your hand on the surface of such a world, you would feel almost no warmth at all, just a memory of heat too faint to matter, radiating outward into a night with no end. There is also the question of whether we could ever really talk to something living on a rogue world, if anything is there at all. No signal has ever been detected, and most researchers do not expect one. Life on a rogue planet, if it exists, would likely be simple and hidden, sealed away in a deep ocean beneath miles of ice, using chemical energy instead of starlight. It would have no reason to broadcast anything, no sky to look up at, no way of knowing it was being searched for. The listening we do is one-sided and may always remain that way. Some scientists wonder about a different kind of search altogether, one that does not look for light or radio waves, but for the subtle gravitational tug a rogue planet exerts as it drifts near other objects. This method is still experimental, more mathematical possibility than working tool. If it develops, It could let us trace the paths of these wandering worlds, the way we trace ripples moving outward from a stone dropped in still water. You would leave no ripple yourself, standing there in that cold, but the world beneath your feet, massive and ancient, would leave one, faint and slow, spreading outward for anyone patient enough to notice. Across the coming centuries, more rogue planets will keep passing near the edges of known star systems, and a few might even be captured, pulled into new orbits around stars they never grew up beside. This has likely already happened many times over the galaxy's long history, though we have no confirmed example yet. It raises a strange thought. A world born in darkness, drifting for millions of years, might someday find itself circling a sun after all, gaining a sky it never had. Whether that would count as an ending or a beginning is not really a question science can answer. For now, the search continues quietly, instrument by instrument, catalogue by catalogue. It could be far higher or lower than any current estimate. If you drifted among them, you would find no signal waiting for you, no beacon marking their locations, only the slow work of careful watching, done by people looking outward into a silence that has not yet decided to answer. Close your eyes and picture your own planet from very far away. Earth is a small blue point, held close to a star that warms it every single day. Somewhere, out past that light, a rogue planet drifts with no such gift. Thinking about that world, quietly, might tell us something about the one under your body right now. Earth did not have to turn out this way. Our solar system formed inside the same crowded, chaotic nursery that flings planets into darkness. Jupiter and Saturn, in their early years, moved and settled into orbits that could have gone very differently. Some models suggest an early planet in our own system may have been ejected long ago, sent drifting the way we imagine rogue worlds drifting now. If that happened, we lost a sibling before we ever had names for such things. You are lying safely in a house tonight, partly because of a gravitational lottery that did not have to favor us. That thought carries a kind of tenderness. It also carries a kind of humility. The stability we take for granted, the sun rising in the same place every morning, is not a universal condition. It is a rare and fragile outcome, one arrangement among many that gravity could have chosen. Some scientists studying planetary formation describe our solar system as unusually calm compared to the systems they find elsewhere. Other researchers are more cautious, noting that we have only studied a small sample of the universe so far, and calm systems may be more common than we think. The truth sits somewhere between those views, still unresolved. Rogue planets, in their silence, also remind us where our raw materials came from. The iron in your blood, the calcium in your bones, the oxygen you are breathing right now as you settle into sleep. All of it was forged inside stars that lived and died long before the sun existed. Supernovae scattered those elements across space, and slowly, over billions of years, gravity gathered some of that scattered material into you. A rogue planet is made of the same stuff. It carries iron and silicon and water ice, born from the same stellar furnaces. The only difference between a rogue world and Earth is the accidental orbit, not the ingredients. If you stood on a rogue planet's frozen crust, your body would feel a cold no place on Earth can produce, a cold reaching down toward absolute zero, the theoretical point where all motion in matter stops. But the atoms inside you, and the atoms inside that faraway planet, share the same ancient origin. You are, in a very real sense, looking at family when you imagine that dark world, distant, changed by circumstance, but built from the same cosmic dust. This is part of why some researchers find rogue planets less lonely than they first appear. If they carry water beneath their ice and warmth from radioactive decay deep in their cores, they may hold the same basic chemistry that life on Earth depends on. Whether that chemistry ever assembles into something living remains an open question, one none of our instruments can answer yet. But the possibility alone reshapes how we think about our own presence here. Maybe warmth from a star was never the only path to a living world. Maybe it is simply the path we happen to take. Widen the view even further, and the picture grows stranger still. Some estimates suggest rogue planets could outnumber the stars in our galaxy, though the true count remains deeply uncertain. If that estimate holds even loosely, then wandering, sunless worlds may be a common outcome of planet formation, not a rare exception. Earth, with its steady orbit and reliable seasons, might be the unusual case. The universe may be filled far more with drifting darkness than with days and nights like ours. You do not need to resolve any of this before sleep tonight. The mystery is not meant to be solved in your mind before you drift off. It is enough to hold the shape of it gently, the way you might hold a stone that is cool and smooth in your palm. Somewhere out past the reach of any telescope, a world drifts in absolute black, made of the same atoms that make up your hands. It has no sun to warm it, no sky to color at dawn, and yet, in the widest possible sense, it is still part of the same story that produced you, the same scattering of stardust, the same patient unfolding of gravity and time. Let that quiet kinship settle over you now, warm and unresolved, as your own small point of light rests safely beneath its star. If you close your eyes now, you can picture one of them, a rogue planet, drifting slow and silent, with no sun to call its own. Picture the surface, dark and cold, maybe wrapped in a thin frost of frozen air. Picture whatever heat still moves far beneath the crust, patient and old, left over from the world's own birth. You have spent this night with worlds like this one. You have let your mind rest on their long, quiet drifting. We still do not know how many of them are out there. Some estimates suggest they could outnumber the stars themselves. Countless dark bodies moving through the space between the lit and named places. Other estimates are far more modest, and the truth may sit somewhere between the two, hidden by how hard these worlds are to see. That gap in our knowledge is not a failure. It is simply where the map runs out. For now, your body can rest easy inside that gap, because some mysteries are allowed to stay open. We do not know either whether life could take hold on such a world. Perhaps deep beneath an ice shell, warmed by a core that still remembers its own formation, something simple stirs in the dark water. Or perhaps every rogue world is exactly as still and empty as it looks from far away. A stone shape with no story inside it. Both ideas remain possible. Both are still waiting for better evidence. You do not have to choose between them tonight. You can hold both gently, the way you might hold two smooth stones in one hand, and let your grip loosen as sleep comes closer. Think one more time of what it would feel like to stand on one of these drifting worlds. There would be no sunrise to wait for, no gold light creeping over a horizon. There would only be stars, thousands of them, cold and pale and far away, giving no warmth at all. Your breath, if you had air to breathe, would hang and settle rather than rise. Your body would learn a stillness deeper than any night you've known on Earth, a stillness with no morning promised at the end of it. And yet even in that stillness, the planet would not be truly alone. It would still be turning, however slowly. It would still be carrying its old heat, its old memory of the star that once held it. It would still be part of the same galaxy that holds our sun, moving along the same great turning disk of light, bound by the same soft pull of gravity that binds everything else. Nothing drifts completely free of the whole. Even a lost world stays inside the larger shape of things. That, maybe, is the quiet gift of this kind of mystery. It asks you to imagine a world with no sun, no day, no warmth from above, and somehow it does not feel frightening. It feels vast and a little tender, the way a dark room feels once your eyes adjust, and you realize you can still make out its shape. The universe holds an uncountable number of these wandering worlds, and it holds you too, here, in your own small bright corner of it, wrapped in air and warmth and the low hum of your own breathing. You do not need an answer tonight. You do not need to know the true number of rogue planets, or whether any of them cradle life in their hidden oceans, or how far the nearest one might be from here. Wonder does not require resolution. It only asks you to notice how big the dark really is, and how many strange, patient, drifting things it might be holding right now, this very moment, while you lie still and let your thoughts grow slower. Somewhere, out past the edges of what we've mapped, a planet with no sun turns once more in its long orbit around nothing at all. It has no name we've given it. It may never cross paths with anything we know, but it is there, most likely, quiet and dark and entirely its own, part of the same night sky you have been picturing all these hours. Let that thought settle over you now, soft as a blanket, and let your body sink into the bed beneath you, the way that planet sinks into its own endless dark. We may learn more about these wandering worlds in the years ahead. We may not. Either way, the not knowing is its own kind of company, wide and quiet, and endless as the space between the stars. For tonight, let the wandering be enough. Let it carry you gently down, past thought, past questions, into rest. Subscribe for a brand new space topic every night. One tap and something incredible is waiting for you tomorrow. Sweet dreams.